Today we're going to talk about resets and synchronizing asynchronous resets. In most systems, what you find is there's just a reset pin coming in and it's treated as an asynchronous reset. In other words, our reset comes in, it fans out to every one of our registers and just feeds the asynchronous clear of all of our registers. And upon assertion of the reset, so in other words, when the reset goes low, all of our registers are going to go to a zero state, and when our reset goes back high, the registers are going to go into normal operation and start operating. And that's the way most systems are implemented. But let's take a look at some possible issues with that design structure. What I've drawn here is a 4-state state machine. We're using one hot encoding, and here is our idle state, 0, 0, 0, 0. And some may look at that and go, hey, that should be 0, 0, 0, 1, because you need one register that is hot. And that's not really, you can use one hot encoding that way. The way Altera is implementing it is with all 4 zeros. In other words, I can look at bit 0 here, and if bit 0 is a 0, because in all other cases it is a 1, I can look at bit 0, and if it is a 0, I know I'm in the idle state, and that by definition is one hot encoding. So in order to implement that in an FPGA, you're going to need 4 registers, which I've drawn over here. Bit 3, bit 2, bit 1, bit 0 is representing bit 3, bit 2, bit 1, bit 0 over here, and a timing diagram showing the resets coming into bit 0 and the reset coming into bit 1. And you'll notice that since it's asynchronous, I've drawn it such that bit 0 reset is right before the clock edge and bit 1 is right after the clock edge. Okay? So when reset is asserted, in this case, our outputs of the flip-flops are going to all be 0, representing the idle state, and we're in idle. Immediately upon release of the reset, the state machine is going to go right into state 1. No other condition is needed. We're going to jump right from idle into state 1. So what's sitting at the input of these registers is a 0, 0, 1, 1 state because we want to go into state 1. So if bit 0 down here sees the release of the reset, the output of this register will go to 1 on this clock edge. This bit 1, the reset shows up just after the rising edge of the clock. So he's not going to see this 1 transfer through. He's still in reset. He's going to stay in a 0 state, and these other registers are going to be in a 0 state, and we're going to be in a 0, 0, 0, 1 state. And if you look, there is no 0, 0, 1 state, and our state machine immediately upon release of the reset is going to get locked up. So how do you get around that? There's a structure that we can use, which is synchronizing the asynchronous reset. So what I've drawn here is a synchronizing stage. So we've got our data input, our clock input coming into all the flip-flops. And what I did is I took the reset down here, and it comes into the asynchronous clear of these registers. And I'm going to clock in a logic 1. Right here, VCC is a logic 1 into this first register, and that's going to clock through to this register here. The output here then feeds all the asynchronous clears inside of the system. And what that allows the circuit to do is, without a clock, we can reset our entire system, because when we asynchronously clear these registers, this output will go to a logic 0, which goes to all the clears, which is going to set all of our registers into a logic low state. Upon release of the reset, when the reset goes high, these circuits, these registers are going to be able to operate properly. We're going to clock through a logic 1 and a logic 1, and these registers are all going to be able to operate normally in a synchronous fashion. And Quartus will analyze this with a recovery removal analysis. So if we go over to Quartus, and I've drawn this into just a schematic diagram, and look into the compilation report, you'll see in the design assistant here that I'm violating Rule 102, which says external reset signals should be synchronized using 2 cascaded registers. And if you look, it is complaining about R3, R2, and R1, which is R3, R2, and R1, which is using the asynchronous reset. So Quartus will monitor that with the Design Assistant and flag you if you are not using a synchronizing system for your resets. I will do a video on recovery removal, so please check back later. Thanks for listening, and have a good day.